surface wave flow, right? So, and then surface, we talking about the beginning of this surface. Let me go back to little bit. At the original for this chapter here. So this chapter here is a surface wave. So this is, we have wave on the surface and would like to know the flow field. Okay, so this is sometimes we call this a surface wave flow. Okay, and at the beginning we are talking about so-called the traveling wave. Okay, and this is traveling wave. Okay, as you can see until here we are starting talking about a traveling wave. So this traveling wave with the waveform will be like this. Okay, epsilon is our amplitude sine 2 pi over lambda x minus ct. Okay, so this wave will travel by this wave speed c. Okay, to the right. Okay, so if you plot this equation, you will see the wave is propagate. Okay, in the x direction. And so we have all the traveling wave solution already. Okay, so this is all the traveling wave solution. Okay, we have stream function, we have a complete potential, we have a path line. Okay, actually the particle path that relate to the path line. Okay, the path line for the, so we know this path line is for the shallow water. Okay, will be elliptic, and then for the deep water liquid, okay, will be circle. So we start to talking about the standing wave. Okay, and as I mentioned before, standing wave can be superimposed by two traveling waves, right? One is a travel to the right, one is travel to the left. This is travel to the right, and this is travel to the left. And by you superimpose these two, you can get a standing wave. The feature for standing waves is very interesting. Is as you can see, there's some point it didn't have any amplitude at all this point here, right? So this is we call this a node. Okay, and then so for that standing wave, we have a specific node, and this node we will not have the oscillation at all. Okay, we're standing at that point. Okay, so that's called a standing wave. And this wave, standing wave, can be superimposed by traveling wave, two traveling wave, A.1 and A.2. So this is A.1, okay, and this is A.2. Only difference is what? Only difference is this here. X minus ct is traveling to the right. X plus ct is traveling to the left. And we also amplitude only 1/2. So we superimpose these two 1/2 amplitude, travel to the right and travel to the left, and then we can superimpose this to get us the standing wave. So this is standing waves for the surface profile. Surface wave look like. Okay, as you can see, epsilon is our amplitude, and then sine, okay, 2 pi x over lambda and cosine omega t. Okay, or 2 pi or cosine 2 pi ft. This omega is equal to 2 pi f here. So as you can see here, okay, when certain x location, okay, for here is our amplitude, right? Because the amplitude times this cosine function give us wave propagate with time, okay? So change with time. So here and here is our amplitude. So at a certain point x, okay, sine of this, okay, will be equal to 0. So this when sine at the x location and for the 2 pi x over lambda sine, okay, equal to 0, that's our node. So and we also introduce you don't have to rewrite the equation or rederive the equation. The reason is what? Because we are using the potential flow. Okay, and potential flow is there's a potential flow. We know the potential flow solution for A.1. We know the potential flow for solution for A.2. So we can superimpose to these two solutions and get a new solution. That's a standing wave solution. Okay, so that's a beautiful thing for the potential flow is a linear equation, and then you can superimpose two solutions we know, okay, and then to construct a new solution, okay. So that's what we try to do here. So this is our traveling wave solution. As you can see, this is Z minus CT. So this is a complete potential, okay, complete potential written by using the traveling waves, okay. So if I want to superimpose, construct the standing wave solution, what should I do? I just follow this. Only the epsilon here become 1/2 epsilon because I amplitude divided by 2. And cosine here, one is Z minus CT, right? And one is Z plus CT here. Okay? So that's it. So once you know this solution, I can superimpose, okay, two traveling wave, okay? One travel to the seed, okay, Z minus CT, and one traveling with a Z plus CT, and I superimpose these two traveling wave, I can get my solution or the complete potential for what? For the standing wave. Okay, so this is a complete potential for a standing wave. Okay, if you direct it from the traveling wave solution, you can have this solution, okay, immediately. And also you can simplify this, okay, as you can see, this is Z minus Z is equals to X plus I, okay, and you can have this one, okay, by using, I think this, okay, or this, okay. As you can see here, we can have the cosine, and inside here we can assume Z plus IH is our alpha, right? And then mass CT here, mass CT, so you have this mass beta. Beta is our CT. So equal to cosine alpha, cosine beta, plus sine alpha, sine beta. So we have a cosine alpha, cosine beta, mass sine alpha, sine beta for the first term here. And for the second term here, again, we do the similar thing. However, this time is a Z plus IH is equal to our alpha. And the CT is our beta. So we have alpha plus beta. So we have to apply this formula here. So this formula gives us a cosine alpha, cosine beta, minus sine alpha, sine beta. So for this term here, we have a cosine alpha, cosine beta, minus sine alpha, sine beta. Okay? And here, since we have a minus sign and plus sign, these two terms will be cancelled. So we'll only have this term here. And as you can see, this term here is almost exact the same, right? And this is a minus 1 plus a minus 1, so minus 2. And then, so this 2 will be cancelled, give you the minus epsilon here. Okay, and the rest of term will be just copied, okay? And this amplitude here, okay? So this is a complete potential. After simplify, we have a complete potential for the standing wave, okay, with a wavelength lambda, and the angular frequency is omega. Omega is equal to 2 pi c over lambda. 2 pi c over lambda is our omega t. Okay, so this term can be as written as omega is our angular frequency. Okay, so now we can write down the complete potential for the standing wave, okay, by using this equation here. Next, we'd like to know what's the path line, okay, inside this flow field. Once we have a standing wave on the top, right? 当我们表面上面有一个驻波存在的时候 okay, the flow field, how the path line inside this flow field. So here is a particle path for a standing wave. Okay, so we'd like to know, okay, because we know the traveling wave. Before we have what? We have this, right? The particle path will be elliptic, okay? Will be like elliptic. And they will degenerate into a circle if you have a deep water liquid, okay? And how about the traveling wave? How about traveling wave? How about a standing wave? Okay? So here we try to do similar analysis as a traveling wave. We define a complete conjugate our flow particle Z1 bar, right? And Z1 bar represent the X1 minus IY1, you should remember. Okay? So the Z1 bar dt is equal to our complete potential derivative dF dz. So we have a complete potential already. This is standing wave complete potential. Okay? We just write here. This is a standing wave complete potential. We just copy to here. OK， 我们把它抄过来。So we do this df dz. So this is first derivative with z. Where is z? Z is here only, right? So sine function become what? Become cosine function here. Okay? Sine function. So we just take a derivative df dz, and then this df dz will be equal to our dz1 bar dt. So this dz1 bar dt will be equal to this. Okay, and we take we integrate, okay, with time, right? So this is z1 bar we can integrate with this time. Where is the time? Time is here, right? Sine 2 pi ct, t is here. So when you integrate sine being cosine, right? Sine change to cosine. Okay? So here is our z1 bar. Okay? z1 bar. As you can see here. Okay? And for z1 bar here, we try to understand. Okay, z1 bar equal to x minus x1 minus minus y1, right? So x1 and y1 is our what? Is our particle path 9 location. Okay, so we try to evaluate this. Okay, and then just try to find the real part and imaginary part for our equation. And here we have the z1 bar. Okay. And for here, as you can see here, cosine 2 pi lambda over times z plus ih. And z plus ih will be equal to x plus I, because z is equal to x plus iy, right? And we have ih, so it become, imaginary part become y plus h here. Okay, for the inside this bracket here. Okay, and so what you can do, if you have this kind of okay, cosine. Okay, cosine, and then so this term here, okay, become 2 pi over lambda, okay, and then x, right, x plus I, y plus h, okay, yes, okay, so you have the cosine 2 pi lambda x, this is the real, okay, plus I, this is I, and 2 pi over lambda y plus h. Okay, like this. So here we have the real part and the imaginary part for it. Okay, and then for this can be using what? For this term here, we can use in this, right? This is the cosine alpha plus beta. So this is our alpha. This is our beta. Okay? If I do that, what happens? Here is okay, we apply this equation for here. Okay, become cosine. Okay, because this is cosine alpha, right? Cosine alpha is what? Alpha is 2 pi x over lambda, 2 pi x over lambda. Multiply cosine beta, beta is this, right? Including I here. And then since this cosine beta here, as you can see here, cosine of this beta is I of this, right? 2 pi over lambda y plus h. And this here, because the cosine I alpha will be equal to hypercosine alpha. Okay, so this will be equal to the hypercosine alpha. Right? Okay, so just apply this too. Okay, so here the cosine alpha is this term, right? And cosine beta here we can return as a become hypercosine of this, hypercosine. Okay, so similar. Okay, sine alpha, this is sine alpha, right? This is sine alpha. And then sine beta we have to apply this because the sine I alpha equal to I sine hypersine alpha. So we have I here, and this is a hypersine alpha. Okay, so this term can be kind of expanded by become like this by apply this three formula here, and you can have this. Okay, and the rest of the equation just copy, right? We have the cosine 2 pi ct here, right? And then here we have an amplitude here. We have amplitude here. Okay, so this is our new Z1 bar. Okay, and the Z1 bar will be, as you can see here. Okay, Z1 bar. Okay, this is our real part, right? Real part, and this is our imaginary part for Z1 bar, right? And we written this Z1 bar in what? In polar coordinate. What do you mean by polar coordinate? Here is where is this? We can written right now. We have the Z1 bar is equal to, for example, this is our real part, right? This number multiplied by this number is our real part. Okay, I'm using the R, R1, plus IM1. Right? This is this number multiplied by this number, and multiplied by this number is our M. Right? So we have real part, imaginary part. This is our Z1 part, and it can be written as what? REIC, right? Okay, and written as RC. This is polar coordinate. Right? And how do you evaluate the R? R is what? R1. R is equal to, so this equal to R1 plus M1. Okay, right? Right? And what's the theta here? Theta is the arctangent of what? Real part divided by imaginary part, M1. So it look like this, right? So we change we know the real part and imaginary part for Z1 part, and we try to change to R theta coordinate. This R theta should look like. Okay. So what we did is just I say in the blackboard here. Okay. So we have we try to express our Z1 bar into the polar coordinate, and we have R1 is potential I theta 1. So this is 1 related to this 1. Okay. Anyway, so R1 should be equal to what? R1 should be equal to square root of R, this real part square plus imaginary part square. Take a square root. Okay. So this is the real part square. So you have this. Okay. You have this. You can check, you can double check. This is this square, right? And this is cosine, hypercosine square. Cosine square, hypercosine square, right? Plus this, right? Sine square plus hypersine square, right? Sine square, hypersine square. Take a square root. Okay? That's exactly what I said. Okay? You can double check with this. Okay? And what's the theta? Theta 1 here. Theta 1 is the arctangent of what? Arctangent of the imaginary part divided by real part, right? And what's the imaginary part? Imaginary part, this part, right? This part. Divided by our what? Real part here. And sine over cosine is what? It's a tangent, right? Hypersine over hypercosine is what? It's a hypertangent, right? So here become the tangent, hypertangent. Okay? Okay, so this is our path line. Okay, we written the path line location. Okay, so Z1 is our path line or particle path. Okay, so as you can see, we can discuss a little bit. Okay, as you can see here, when I have any location for a given location x and y. Okay, I give x and y. What happened? I already can decide this theta 1 already, right? Give me the x location and y location in the full field. Okay, and so theta 1 will be equal to a constant for given x and y. Can you see that? Okay, and then what happened to R1? R1 when you give me the given x and y location. Okay, x y location. So this is okay, already has a constant. However, we have a cosine 2 pi ct here, right? And the cosine 2 pi ct here will be changed with time. Okay, so R1 will be changed with time. Okay, however, theta is a constant for given x and y. Okay, so that will be very interesting. Okay, as you can see here, Okay, once I give a given x and y location, for example, here. Okay, this is just R1 and theta 1. We just write these two equations from the previous transparency. Okay, as you can see here, okay, when x equal to n lambda over 2, okay, this is this spatial. Okay, when x equal to this, what happened? Okay, because the tangent of this here, if you plot this theta 1 formula here, give me the x here, and x can be applied to here, right? So x equal to n lambda over 2, and n lambda over 2 here, tangent, okay, will be equal, this one will be equal to 0, okay? So arctangent of 0 will be, give you, this theta 1 will be 0 or pi. Okay, this theta 1 will be 0. And then if you check, okay, where is the location for our x equal to n lambda over 2? Here is when n equal to 0 is x equal to 0 is our, okay, location is here, right? X equal to 0 is location is here. And when n equal to 1, what happened? X equal to lambda over 2 just half wavelength, right? This is one wavelength. So this is one half the wavelength, so it should be here, right? This is one wavelength, okay, and this is half wavelength. So x equal to lambda over 2 is here, okay, and n equal to 2 become x equal to lambda will be here. So at these three locations, x equal to 0, x equal to lambda over 2, and x equal to lambda, what happened? Our theta 1 will be equal to what? Equal to 0 or pi. What happened? What's the physical meaning? The theta 1 equals 0 in pi. That's our path line, right? And the path line means at this location here, it only move in the theta 1, the theta 1 equal to 0 or pi. That means they are moving horizontal. This is 0 direction. This is the pi direction, right? So they will move back and forth like this. All the fluid particle at this location or this location and this location, all the fluid particle move just back and forth horizontally. OK， 它们只会水平的移动，左右移动而已，在这些特殊的点上面。OK， in this all this spatial location, OK, with our fluid particle, OK, only move, OK, horizontally, OK, since our theta 1 is a constant, either equal to 0 or pi. OK, let's check another point. OK, if your x is equal to this, what happens? Equal to this 2 pi plus 1 over lambda over 4, okay, times lambda over 4. Let's apply, okay, when n equal to 0, what happens? N equal to 0 is what? Is x equal to lambda over 4, right? Where is lambda over 4? Lambda over 4 is here. Lambda over 4 is here. Okay, lambda over 4. This is 1/2. Okay, this is quarter of wavelength here. N equal to 2 give you the, okay, 3/4, okay, lambda, right? So here is the location. As you can see, if you apply x equal to n, is this, okay, x equal to 2n plus 1 times lambda over 4 into our theta 1, this formula here, what happened? Here is a 2 pi x times this give you the infinity, okay, because our arctangent infinity is what? Only theta 1 can be happen is what? Is a pi over 2 or 3 pi over 2. Okay? So at this location here, at this certain location, okay, the green line here, the green location here, okay, this marked with green location in the green location here, you only move in a 2 pi over 2 or 3 pi over 2. That means they are moved, okay, upward or back or downward direction, right? Okay, so the particle at a certain location only move, okay, for this location only move downward and upward location. That's vertical motion, oscillation. And for this location, they move only horizontally, okay, back and forth. Okay, what happened to the, okay, not this specific, if the location here, what happened? You can guess. You will move like certain angle, right? With a certain angle, okay? With the slope, okay? With a slope certain angle, okay? So that will be very interesting to see, okay? So we, in a standing wave, as you can see, we define, okay, for this point, we call this is node, right? Node means there is no, okay, amplitude at all. We're standing at that point, right? So standing wave at the node position, okay? As you can see here, the particle pass at the node position, they only move back and forth in the horizontal direction, okay? And then if in the quarter wavelengths here, okay, this is quarter wavelengths and the 3/4 here, okay, we call this node is called anti-node, okay, and for the anti-node here, our full particle only move vertically back and forth, right? That's oscillation in the vertical direction, okay, and here is give you the picture, okay, how do you define a node and anti-node, okay? With a maximum amplitude location, we call this anti-node. With amplitude equal to 0 is a node position for standing wave. Okay, so you have the picture, okay, like this. So we know what the particle, okay, pass line, okay, inside this flow field when we have a standing wave above. Okay, 当我们有个表面有一个驻波存在的时候，下面的流场要怎么样流？下面的一些那个 pass line 要怎么样变化 ？Okay, so this is just under the standing wave. Okay, we have this conclusion here. Okay, next we will apply this to some physical problem. Okay, one physical problem, okay, you may have is called is a wave in the rectangular vessel. Okay, so we have this physical problem is that instead of the previous, okay, we don't have this boundary, right? This boundary is in the infinity. Okay, and right now we have this boundary. Okay, so we become our flow inside a rectangular, okay, container, right? So once you have a wave generally inside this rectangular container, inside here, okay, and our coordinate system, our x, should be y. Check. Make a mistake here. Okay. So this is our coordinate system. Okay, coordinate system. Okay, and we have a kind of a rectangular container, and try to see the water, what kind of wave can be generated inside this rectangular tank. Okay, and what's the Gabor equation we have? We apply. Okay, our Gabor equation is the Laplace equation, which since we are assume this flow is implicit, incompressible, irrotational, right? So we're using the velocity potential. Okay, and this velocity potential should satisfy the Laplace equation. This is our Gabor equation. And for this physical problem, as you can see here, our boundary condition will slightly change. Okay, we have this boundary condition and this boundary and this boundary condition, right? And on the free surface here, we also have the dynamic boundary condition. Okay, so our height of the water is h. So when y equal to h, okay, this is our dynamic boundary condition as before. Okay, this is our dynamic boundary condition. And when y equal to 0, well, when y equal to 0, that's a bottom wall, right? Bottom wall boundary condition. Bottom wall boundary condition, how do you specify? There is no flow penetrate, right? There's a key word, right? Penetrate into the wall. Okay, they can sliding, okay, tangential to the wall, but there is no flow across the wall. That's a potential flow, okay, boundary condition. You have to, okay, well known of this, okay. So this direction is a v direction. V direction is a partial v, partial y, right? That's equal to v. When y equal to 0, that's here, right? Y equal to 0 on the bottom wall here. Our v velocity should be equal to 0. That means there is no flow, okay, penetrate or close our wall, okay, bottom wall here. And what happened here and here? We also have the same stimulus boundary condition, right? And this for here, boundary condition is what? When x equal to L, right? X equal to positive L. And here, what's the boundary condition? X equal to minus L, right? This is minus L. And what's the two boundary condition should be satisfied for these two